Hello, everybody. This lesson today is about the physics and sound of pitch. So it's part of a two-video series about how physics and acoustics and the physics profile of a sound affect how we sing. So hopefully by the end of these two videos, you can get some tips on how to improve your singing and think about how your choral sound works based on the science of how of acoustics work. Some of the stuff that I'll be doing in these videos is like a demonstration that we would normally do in class with volunteers, but I will do my best to demonstrate them in different ways on the camera. Otherwise, sometimes you'll have to just use your imagination. So let's get into it. All right, what do you need to know about acoustics? Well, first off, we got to talk about what sound is. Okay, and sound ultimately is vibrations. Okay, it's vibrations that move through the air. They move from the source of the sound. Okay, so the source of the sound, whether that's a clap or a piano playing or a guitar string vibrating, right? It creates vibrations. Those vibrations move through the air. They're technically compression waves. We don't really need to get into what that is, okay? But they move through the air and they hit your ear. They make little bones in your ear vibrate. And those bones vibrations, they get translated into electrical signals that go into your brain, and then you interpret them as sound. So really it's vibration over here. That air vibrates through the air to your ear then vibrates because it's getting hit by this sound vibrations, and then that is turned into electrical signals that go into your brain. Bada bing, we get sound. Okay, same thing works as a microphone. Basically it's the same kind of thing. I'm making a vibration with my vocal cords coming out. It's vibrating a little membrane on the microphone, and that is going into the computer through electrical signals, getting digitized and turns into beeps and boops, and then we get our sound. Now the way that we visualize it is a graph like this, two-dimensional. Now I just said a little bit ago that the sound is compression waves, so they kind of exist in three-dimensional space, but when we visualize them, we like to use this kind of thing. Now what we're looking at right here is called a sine wave. A sine wave is kind of an unnatural sound. It's the purest form of sound that we can get, at least graphically. Okay, and it sounds like this. We can get pretty close with our voices. Okay, but that's a sine wave. Okay, so that's what something that it would make a waveform on a graph that looks like this. Okay, on a wave we have peaks, we've got valleys. It's not marked on here, but the the up and down is what's called amplitude, and the side to side. So the y-axis and the x-axis is time. So this is the volume over time. Okay, so amplitude is a word I just used. The amplitude is the height of the waveform. Okay, we're going to keep referring back to these waveforms because it's just the way that we graphically visualize it. So the height is called amplitude. The amplitude is basically the volume. Okay, so a louder sound is going to make a higher, or I should almost like more like a wider amplitude. So above here we would do positive, below is negative, and the wider range we have, the louder it's going to be, and then a lower amplitude is going to mean that it's a softer sound. Okay, that seems pretty easy. Amplitude, higher means louder, lower means softer. Then we have wavelength. Okay, the wavelength is the distance from one. We just usually go from the peak to the next peak. Okay, so that's our wavelength. All right, so amplitude, wavelength. Now you may have heard the term wavelength before, okay, because we use that term wavelength not just to mean for sound, but also very often for light and color. Okay, but I guess really just light. What wavelength can we see? But in sound, we use this term a little bit less, actually, and we'll get to that in a second. Because it has to do with what's called frequency. Right now, normally I would get 2 volunteers to do this, but this particular one, we're just going to have to use our imagination. Okay, but I think I can help you out using your imagination to figure this one out. All right, so we have one person who's going to represent a low instrument, a bass, in this example, and then a second person who's going to represent, let's say, a piccolo or a high soprano, is what we would probably do in the room. Okay, so we've got our bass up here and our high soprano down here. Now, what they're going to do is they're going to walk across this space. Okay, the bass is going to take big steps. Those big steps are going to represent long wavelengths. Okay, so a long distance between peak to peak on the wavelength. And the higher instrument is going to represent a shorter wavelength. Okay, now they're going to walk from this end of the room to the next end of the room, but they're going to try to get across that distance. The big wavelength is going to take as big as steps as possible. Our short wavelength is going to take as tiny steps as possible. And so you can imagine how many fewer steps the big wavelength is going to take than the small wavelength. Okay, our bass is going to take fewer steps than the piccolo. A longer stride means fewer steps needed to reach the goal. Shorter stride means more steps needed to reach the goal. Okay, so let's say our bass can get there in about, I don't know, 5 steps. The piccolo is going to take 70 steps to get there. That seems a little, that's probably a little exaggerated, but you get the idea. Okay. They get across the room. Now, imagine them doing it at the exact, they want to get from one end of the room to the opposite end of the room in the same amount of time. Okay, so we're going from here to here in the same amount of time, but the bass is taking big steps and the piccolo is taking little tiny steps. Okay, which one has to move more or go faster to get from this end of the room to this end of the room? Right, that is going to be the piccolo. It's going to take a lot more steps, go a lot faster, quote unquote. The term that I'm working around is called frequency. Okay, it's the number of waves or steps if we're thinking about these guys. Okay, the frequency is the number of vibrations or steps per second that it takes to get from, number of waves per second. Okay, so let's say that our bass, if we think of getting from one end of the room to the other end of the room is 1 second. I know I'm mixing space and time here. Okay, but you can all be little Stephen Hawkins and figure it out. All right, so we're going from here to here, right? That's 1 second. It takes the bass way fewer vibrations and the piccolo a lot more vibrations to get from here to here in 1 second. That is what we're getting at. Okay, so a low frequency is what we call the bass. A low frequency, because it doesn't take as many vibrations, and a high frequency takes a lot more vibrations. Okay, low frequency equals low pitch, high frequency equals higher pitch. That is where pitch ultimately comes from, because the number of vibrations per second, when we measure that in hertz. So, back up a little bit. Amplitude is the volume. You don't really need to memorize wavelength for sound, okay? We mostly talk about frequency, because that's how it relates to pitch. Amplitude is volume, frequency is pitch. Now, the reason that we're using these scientific terms is because I want to get us out of thinking about these things as just abstract concepts and more about things that happen in real time in the physical world. Okay, so there we go. Low frequency, low pitch, high frequency, high pitch. Okay, lower pitches require a lower or slower frequency. High pitches require a faster or higher frequency. Got it. Thank you to our volunteers who don't exist right now. All right, we're gonna do another experiment. Okay, I'm gonna get pull up a metronome. Okay, and then if we were doing this in the space, I'd have a volunteer, but it's just gonna be me. Okay, I'm gonna be clapping very quickly. Okay, so let me get my metronome out here. Okay, and my metronome, I'm going to set my metronome for 60. Okay, because that represents 1 beat per second. Okay, so that represents a hertz. Okay, so that is a frequency of 1 hertz. Now, I'm going to clap 1 hertz. All right, you get the idea, right? Okay, so that's my 1 hertz clap. Here's my 2 hertz clap. Go. Four hertz. Maybe a little bit harder. All right, now, do you think I can do, the next goal would be 8 hertz. So 8 hertz is a lot harder. And 16 hertz. Yeah, I can't, if I'm just like tapping my fingers, I can't do it, right? So that's 16 hertz. Okay, is impossible for me to physically do. All right. All right, so each clap is equal to 1 hertz. I can maybe get 8 hertz. The lowest note on the piano is 27 hertz. Okay, so imagine that you could clap your hands 27 times per second. You theoretically could make that note. Theoretically. Okay, but, I mean, it doesn't necessarily always work that way, but all right, this is a frequency chart of all the different instruments, not all the different instruments, but many of the most common Western classical music instruments, at least. Okay, you'll notice maybe up at the top we have the treble vocals and bass vocals. Okay, the lower treble vocals start at 200 hertz. That means that your vocal folds are vibrating against each other 200 times per second for your low notes. Okay, up at the top of the range, 1.2 kilohertz. That means 1,200 times per second. This is how fast things go, okay? If I play the high notes on a piano, that's 3.1. I got a little feedback there, sorry. That was 3,100 vibrations per second. That is some fast vibrations. Okay, here's a frequency chart as shown on the piano. Okay, the only reason I put this on here is I want to show you. Let's see, can we see? Yeah, so here's A. Now this is not the lowest A. I don't know if I can get the lowest A on here. That's okay. The lowest. Here's the low A. That's 110 hertz. You see the A below that? No. Down at the bottom, right? That was a 27.5 hertz. Okay, but this A, 110. 220, 440. Okay, the reason I want to show this is that when we go up an octave, okay, we double the frequency for each octave, for each note. So each octave that we go up, the number of vibrations per second doubles. And so we have this ramping up. Let me demonstrate this one. We have this ramping up of how fast our vibrations go. So that's how we can end up with, on the low end it's 200 vibrations per second, on the high end it's 1.2 kilohertz, 1,200 times per second. Okay. The reason I'm showing all this, I just want you to see like how fast things are vibrating when you're talking, when you're singing. Okay, it's super, super fast. Okay, now what happens when we sing? We've been over this a little bit before. But all right, now this is one that I usually need someone else to do, but I can do it with a guitar. Okay, so what happens when we sing? Sorry for my out of tune guitar. All right, you got to remember. Okay, we've got our heavy muscle and our light muscle. This is from one of the other lessons that we've done here. Okay, and these white things right here that look like bones, those are actually your vocal folds. You can think of them right now as your vocal folds. Your heavy muscle makes your vocal folds shorter and thicker. The light muscle makes your vocal folds longer and thinner. Okay, when our vocal folds are lengthened and thin, they vibrate faster and create higher pitches. So think about, all right, I've got a guitar string. Now, your vocal folds are actually vibrating against each other, and the guitar string is just one string, right? But if you think of this string vibrating as your vocal folds, okay? If I tune it down, where I am making, right now I'm loosening up the tuning machine up here, okay? And it's making the string shorter. It's not really making it that much thicker, but I mean, it actually is, you just can't see it. Okay? I'm making it shorter by tuning it down. Now you can't see it, but it actually, I mean, sort of is getting shorter. Okay? Versus, bring it up, making it tighter, tauter, and technically longer. Okay? The reason it's technically longer is because it's coiled up there, so I'm stretching it out. Now you can think of doing the same thing with a rubber band, right? It's just kind of hard to demonstrate all by myself, right? So I've got a rubber band here, right? And if I'm making it's short right now, it is not able to create enough vibrations per second to us to even hear it. But if I make it longer, you can start to hear some pitches, right? If I make it really taut, getting some resistance training out here too, right? If I make that rubber band really taut, then I can actually start to hear pitches and they start to go up. When I squeeze it back down, the pitches get lower because I am creating more vibrations per second as it gets longer and tauter, and fewer vibrations per second as it's getting shorter and thicker. Okay, that is how it relates to our singing. When our vocal folds are shortened and thickened, they create lower pitches. When they are lengthened and thinned, they create faster and higher vibrations and pitches. Okay, so the takeaways that I want you to get from this. Number one, sound is vibrations. Okay, that is what it is, all it is. Sound is vibrations. It's not magic, it's vibrations. For music, the main terms we use are amplitude, which refers to the volume, and frequency, which refers to the pitch. Low pitches are slower frequencies, high pitches are faster frequencies. You can have a higher pitch that is a low amplitude. Okay, they are not necessarily related to each other. For singing though, sometimes it's easier to do certain things in certain ways. But even at the bottom of our range, our vocal folds are vibrating very quickly, right? Remember that? On the low end, your, let's see if I can find that graphic again. Okay, on the low end, your voice is still vibrating around 100. This is for a bass singer, right? 100 hertz would be down there or about, okay? Even on the low end, it's still super, super fast. And if you're thinking, well, 100 isn't as high as 3,000, no. Good math, right? 100 is not as high as 3,000, but can you clap your hands 100 times per second? Like, that's fast. It's really fast. It's hard to even imagine something happening 100 times per second. Okay. So remember that it's all about vibrations, and that your vocal folds are vibrating against each other to make that sound very, very fast. And so how do we apply this to singing? Also, like kid's vocal form. Leave something to be desired, but cute shirt. All right, singing applications. This is probably one of my biggest things. Okay, there are no such thing as high and low notes. There's no such thing as high notes and low notes. Those terms are ones that we use all the time, but they don't really mean anything, right? There's no such thing as a high note. A high note is actually a faster frequency, or a higher frequency. A low note is a slower frequency. But the issue that we have when we talk about high notes and low notes is when we go for high notes, right? Think about what people do physically when they try to sing a high note. They do what this kid's doing, right? I would guarantee this kid is going for a high note right now. Okay, so when we go for high notes, we tend to stretch up, and that's really bad for our voices, and it doesn't actually help us hit the pitches. So when we think, I like to think of instead of a high note, it's a faster frequency. Okay, a low note, people often tuck their chins in when they're going for low notes. Also, not helpful for singing. Right, so there's no such thing as high notes or low notes. They're just faster and slower frequencies. Okay. Your vocal range and timbre are determined by your biology, training, health, and hormones. That's kind of more of a thing that we're going to get to in the next session. And then just remember that it's physics. Okay, these things are all physics. The reason I like to go back to the science of it is because then we can remember, like, it's not that you can't hit your pitches because you're broken. It's that you have to learn, you have to train your vocal folds to hit these frequencies. Now, there are some frequencies that you are not going to hit, right? Like, we're not going to be able to sing probably below, I mean, that low note on the piano, like, there might be a human out there who can sing that. But you would just, it would sound gnarly. It would more sound like vocal fry than anything else. Vocal fry is the, right? But you're probably not going to be able to hit that. So there's certain notes, and we're not going to be able to sing way up there, right? Where, like, dogs are going to start barking down the street. But the other pitches, like, it's all just physics. That means you can get there. You can get there. Okay. For the next video, we're going to talk about resonance, overtones, and shaping your sound. Okay, so that one is kind of a deeper level of physics than this one, but I don't think it's out of range for just a basic understanding, because really what we're trying to do is understand these things, the basics, so that we can apply them to our singing and apply them to our choral sound and the rest of our music, and we can use them to make good musical choices as we are performing and as we are working on honing our craft. So anyway, that is it for today. Thank you for watching this and for sticking around, and I'll see you next time. Bye-bye.